Good evening. So this is one of the final presentations. I'm Simon, MSA student and research assistant at FHNW, together with Fabian, he's also research assistant. And for the past half year, we have been working together with our industrial partner, Anapico, in the test and measurement industry to evaluate super fast protocols, 100 gigabit protocols. And we are here today to dive into the matter of why we would want to have such high speeds in industrial applications. Then find out what is already out there, the different technologies and protocols that are available. And finally, the one we picked, RoCE, kind of, that's how you say it, RoCE, gonna punch industrial applications to 100 gigabits per second. So high-speed data first. Why do we want to go this fast? Because we have 10G Ethernet or 1G Ethernet or 100 or slower or USB. Why would we need such high data rates? Well, there's three main application scenarios or categories where you would want to use such high speeds. So first that comes to mind is acquisition. So for example, cameras. And today we have increasingly higher resolutions, higher frame rates. And as a matter of fact, at our institute we had a similar project which was dealing with high-speed camera and the data processing of it. And for several constraint reasons, the processing was not able to be done right next to the camera. So the data needs to move somewhere else for processing, just a couple of meters away. But still, a camera at this resolution and frame rates may produce data rates of up to 40 gigabits per second already. So there's one application scenario. The next one is data processing, as I have already mentioned. And here you would think of cloud computing, data centers, high performance computing. This is also the industry that came up with most of the protocols of 100G and above. So definitely here's an application scenario. And finally, kind of the topic that our industrial partner was interested in was data generation. I have here another example of digital to analog converter. It was an eval board from Analog Devices. And this particular chip runs at 12 gigasamples and a 16-bit resolution. And as you may see, that adds up quite significantly. It's no problem if you have an FPGA on the board and some serial connection like Chest 204B, then it's easy peasy to get that kind of data moved around on the PCB. But now what if your data does not come from the FPGA, but from somewhere remotely, like a computer, a workstation computer, a regular computer, which was a very important key aspect of this project, to have best flexibility. So, these are the three key areas. How do we transport all that data? And of course, in engineering, we don't want to reinvent the wheel all the time. So we look for what is already out there. And if we are in research, we also might peek into what other researchers are doing. And first I came up to several papers from the CERN, because of course the particle accelerator and particle physics, they have experiments with a lot of measurement data that needs to be transferred to the storage for later analysis. And they came up with Felix front-end link exchange, which is a custom front-end in optical fibers. And they have a custom PCB for that. And then they go into the backend via PCIe Express to also use then 50 gigabit Ethernet or 100 gigabit Ethernet. So we're not completely off with Ethernet. Now, that's not exactly what we're looking for with a custom PCB and custom optical links and stuff. So we want to use industrial standards. So what do we have on the market? First of all, we have something like CPRI, Common Public Radio Interface. That's a protocol from the telecommunication industry for very specifically IQ data streams, because you have to imagine somewhere you have your antenna, and very close to it you have the analog hardware responsible for the signal. But the digital data signals, they are somewhere in a white box on a data hub site. And you need to connect the antenna front end with this hub site over some fiber channels for several tens of meters. And they use CPRI. And it has data rates that are around that 100G or 40, 50G. But it's a very specific use case, not exactly what we were looking for, very restricted to one industry only. So we were looking at other options, and there's chip-to-chip or board-to-board interfaces. For example, Interlaken is quite common. It goes up to 600 gigabits. If you have one single PCB with several chips on it, and they need to interface with each other. And then you also have, from Xilinx specifically, you have Aurora. But the problem with these protocols is they are very, very simple. There's no routing or error correction, or not a lot thereof. Very short distances, board to board. And it's very custom, so you won't find a PCIe card you can plug into your computer and just interface with your FPGA board, which is an important aspect. Next thing we found is the optical digital interface, ODI, from Keysight Technologies. And this sounds oddly perfect. It has acquisition, processing, and generation in their use case. So it sort of covers all of what we want. And they also have exactly the digitizer, storage, and generation of signals in their description of the standard. And it's used in RF instrumentation. The problem with this protocol still is there's no PCIe card you can plug into your PC. And even though they state it is open, it's still heavily controlled by Keysight. The first time development costs are quite high because you have to buy into their rack systems and their custom hardware to even begin with. So we don't want that. What else is there? I started listing all of these protocols in this table, and you can see right down here at the bottom, I have as a requirement that it has some sort of PCIe card available for your computer. And as another factor is, because we're working with Xilinx technology, is if a suitable IP core is available on the market to make development easier. And then a few other aspects. So with industrial standards, what is the connector standard? Most of them use QSFP+. There's also some optical stuff going on. And if it is routable or not, which was not really relevant to us, but for some people it may be. But we then found the InfiniBand family of protocols, which is this very specific Ethernet. It goes towards Ethernet, but Fabian can tell you more about this.
Thank you very much, Simon. Did any one of you ever heard of RoCE? Perfect. So you are the right candidates for my presentation, or for my part of the presentation. Little disclaimer, I will only talk about the top of the iceberg. RoCE is a complex protocol and it has a very steep learning curve, especially in developing applications. RoCE is short for RDMA over Converged Ethernet. Converged Ethernet is an expands the Ethernet network standard and also allows clustering data and storage data over the Ethernet network. And RDMA stands for Remote Direct Memory Access, the main technology behind this RoCE protocol. Here is an image of how the RoCE protocol, or the Remote Direct Memory Access, works. On the left, we have an Ethernet network coupled directly to the CPU, and the CPU manages the memory. So here's the big bottleneck here is the CPU. Now we want to remove this bottleneck to have to get more bandwidth, and So the Ethernet network directly accesses the memory via the north and the south bridge of a motherboard, for example, in a computer. Now, why did we choose RoCE? The main two reasons were because there is a PCI Ethernet card for a computer, for example, the one here we're using, and there is hardware and an IP core for an FPGA, because we needed to generate the data on a personal computer and send it very fast to an FPGA. So there weren't any other solutions which we could work with. Yeah. So, but now why RoCE? RoCE is an Ethernet-based standard, so it can operate basically over every Ethernet network. It comes from the server and data environment, so there is already an Ethernet standard with very high bandwidth capability. So they don't need to upgrade those Ethernet networks to use RoCE for their environment. And now the main 2 points for us is that RoCE is able to move data directly between the memory of two remote hosts, as I described earlier. And in this, the result of this, by bypassing the CPU and removing the bottleneck of the CPU, we're getting very low latencies and very high bandwidths. For example, NVIDIA just released a few weeks ago a PCIe card, Gen 6, I'm not sure if it's Gen 6 or Gen 5, with bandwidths up to 400 gigabit per second. Our PCIe card is capable of 100 gigabit per second. Now to the hardware on which support RoCE or the remote direct memory access is on the server side, on the left, or on the computer side, an NVIDIA network interface card. NVIDIA is the only supplier which supports RoCE or RDMA cards, and this specific card has a dual port with 100 gigabit per second bandwidth. And on the right side is an Xilinx development board with an UltraScale Plus FPGA with quad ports, 4 ports with 100 gigabit capable ports. Yes, so you can't use standard Ethernet connectors for this. You have to use other types with higher bandwidths. There is an Ethernet standard or an Ethernet connection standard for this. Those are the SFP connectors. They're called small form factor pluggable connectors, and there are different varieties of different models. For our solution, we're using the quad SFP28 to reach the promised 100 gigabit per second. Now you have to use a cable. There are fiber and copper cable. Fiber cables are a little bit more expensive, but you can have longer data lines and you can operate in environments with electrical disturbances. We tested both. We tested fiber cables, and I have here a short copper cable. They were restricted to about 2 meters. Both worked, and yeah. And now to our application example. As I said earlier, we had a computer. This is, in our case, the master, or in network language, the client, and the FPGA board, the slave, or in the networking language, the server. The personal computer sends the data in a DDR memory to the FPGA board. We were able to stream the data continuously into the DDR memory. We have to say that we only had write access to the DDR memory, so the server only was writing to the DDR memory. There weren't any read access from the FPGA, so we had no bottleneck on the side of the memory access on the FPGA board. We made some speed tests. We were able to do some loopback speed tests on the PCI card itself because it has dual ports. And we were able to do some speed tests from the computer to the FPGA. Now, when we see this graph on the y-axis, we have the bandwidth in gigabits per second. On the x-axis, we have a length per RDMA write. RDMA write is the operation of RoCE, which writes data from the memory of the server, from the memory of the client to the server, so from the computer to the FPGA board. And you have to imagine the length of the RDMA write. For example, if you have 1 terabyte of memory or 100 gigabyte of memory you want to send, you will slice it up into packet sizes. And the result of this is the length of those packet sizes. There are optimal packet sizes you can use, about 50 to 50 megabyte to 1 gigabyte. And we had a result of about 92 gigabits per second. This result was very consistent, and we were able to repeat those same results. Yeah, now I will give the word back to Simon about latency tests.
Thank you. One word about the speed test. We achieved 92 gigabits per second. That's also consistent with the literature, because practical limitation of 100G Ethernet is around 95 gigabits per second, just because of protocol overhead and sort of that stuff. Yeah, latency, because you always read in the Xilinx documentation, it's low latency, low latency, low latency, but no numbers. So we tested that as well. So this is a loopback scenario on the FPGA, so from one to the other QSFP port. And we are streaming data out of the DDR4 memory back into the DDR4 memory. And there are 2 different Xilinx IP cores involved. The ERNIC, Embedded Remote NIC, which handles the whole RoCE protocol. And then we have the CMAC, the 100G MAC, which then does the translation to the physical layer. And the network latency is around 300 nanoseconds, which is consistent with what you read from other manufacturers of InfiniBand switches, for example. So they have several 100 nanoseconds of latency. And then the receive processing of the ERNIC, it depends a little bit on how you implement it, and there's also a FIFO involved. So we ended up with around 800 nanoseconds of that. So we are at around 1.1 microseconds for this latency. We still got time. So bonus slides, haha. Bottlenecks, which may also be interesting for such a application scenario. So we have on one side the PC, and there it depends a little bit on AMD or Intel, but you have some sort of memory architecture with the memory controller and also the PCIe bus, of course. And in our case, we had the PCI Gen 3 at 16 lanes. So this network card uses all 16 lanes. Depending on your computer hardware, you may not have a graphics card or storage controllers anymore, because that's all used for your network. But PCIe Gen 3 at 16 lanes has 120 gigabits of bandwidth per channel, so read and write is separate. And then the DDR memory is a bit higher, depends on your memory speeds and numbers of memories installed, but you should be higher than that. In between you have 100 gigabits as per standard, and then on the FPGA side it gets a little bit trickier, because you have the DDR4 memory and a memory controller, but this is one way only. So you have a memory arbiter, which multiplexes between read and write accesses. And if you're not careful with what you do with your DDR memory, for example, the ERNIC has a lot of status memory or status registers that's stored in the DDR memory, you run into trouble, into bottlenecks, where the incoming data will be blocked by the arbiter. And then you get significant drops of data rate, and that's not good. But you can circumvent that by installing a FIFO here in the data channel, and which increases your latency, but at least you're consistent with the speed. That's about it. Yeah. Do you have any questions?